Hey folks, welcome to Digimento Education. This is Analogs, Electronics and Circuits Lecture 4. Hopefully you must have gone through the last 3 lectures that I covered and are well versed until now with the concepts which I marked separately as important. Okay, let's begin with this lecture. So first I will request you to please hit the like button if you really like this video, share and subscribe to our channel and write down your comments below. Okay. Now, so we basically ended our last lecture with the discussion of the V diode DC voltage. Now we are going to discuss about the no load output DC voltage when we take RL infinity, or we can say that IDC is equal to 0. So since we are considering the DC, we are performing the DC analysis in this case. So we have a look at the second part of the circuit where we have this. Okay, we are considering only one diode at a time, and we can say that this RL tends to infinity, which means that IDC here is equal to 0. So since we are talking of DC, the voltage present here is purely AC. So we can say the voltage here is 0 volts. This is a DC voltage across the secondary winding of the transformer is equal to 0. So because the voltage that is DC. So this is V diode DC, and this will be equal to VDC NL no load. So if we apply the KVL here, so applying the KVL, if you just see, you get -0 plus V diode DC plus VDC NL is equal to 0. So we can say that VDC NL is minus V diode DC. So we get VDC NL. What was V diode? Minus 2 Vm by pi. As we derived earlier in the last lecture, it will be equal to 2 Vm by pi. So we can say VDC NL is 2 Vm by pi. This is the no load output voltage. Okay, this is no load output voltage. I think it was the 9th point. Okay, understood. Now let's discuss the 10th point, 10th topic. It's basically full load output voltage. Full load output DC voltage. Full load output DC voltage, which is VDC FL. So VDC FL will be when RL is not equal to 0. Okay, when RL is not equal to 0, that's basically VDC FL is basically VDC or output voltage when RL is not equal to infinity, neither it is equal to 0, or we can say IDC is not equal to 0. So we get VDC FL is IDC into RL and is also equal to VDC NL minus IDC into R, where R is equal to RF plus RSW by 2. Why RSW by 2? Because we know for the secondary winding, since it is center tabbed, this is RSW, this portion will be RSW by 2, this will be RSW by 2. Okay, there will be a DC power dissipation across the secondary winding because the voltage is a pure AC, but the current is not pure AC. There is a DC current is still flowing in that. Okay, so VDC FL will be equal to IDC into RL, VDC NL minus IDC into R. Or you can write VDC FL is IDC into RL, VDC NL is 2 Vm by pi minus IDC into R. We can basically approximate it to a Thevenin equivalent, where the 2 Vm by pi is VTH and R is basically your RTH. Okay, this will be equal to IDC into R is the output voltage. Okay, so this is how it goes. So we are considering it for only for one diode. The other is true. This expression is also true for the other diode. Okay. Now, regulation factor. Next one is the regulation factor. Regulation factor. So this will be this is regulation factor. We define the regulation factor as VDC-NL minus VDC-FL upon VDC-FL. So the expression will remain the same. So percentage regulation. So percentage regulation will be equal to R upon RL into 100%. But the major difference being, the only difference being R is equal to RSW by 2 plus RF. Okay. This is the percentage regulation. This is what it okay. Now next one is basically the Thevenin equivalent of the circuit. We have then the Thevenin equivalent. Thevenin equivalent of the circuit. So this is how it represents the Thevenin equivalent. So Thevenin equivalent, so we know this is VDC-FL is 2 Vm by pi minus IDC into R. Okay, so this will be equal to V Thevenin and this will be equal to R Thevenin. So we can approximate this thing to this circuit. So this will be V Thevenin, this is R Thevenin, and this is a load resistance RL. Okay, this is VDC-FL, this is IDC, this is R Thevenin, which is equal to R in this case, and this is V Thevenin, which is 2 Vm by pi. So this is basically Thevenin equivalent of a full wave rectifier or a center-tap full wave rectifier. This is how it looks. Okay, the Thevenin equivalent circuit of the full wave rectifier. Now let's discuss about the peak inverse voltage, because this is important. Peak inverse voltage, as we already discussed, should be as small as possible, so that because if we have to peak inverse voltage should be as small as possible, so as not to let the voltage go beyond particular designed voltage, particular limited voltage of a diode, so that the diode does not get damaged. Okay, so otherwise if peak inverse voltage is very high, you require a high breakdown voltage wala diode, which is also costly. So peak inverse voltage should be as small as possible. That should lie between the breakdown voltage and zero region. Okay, that's one thing that we have to keep in mind. Point of discussion is peak inverse voltage, which we define as PIV. So peak inverse voltage is the maximum inverse voltage of a diode across a diode. So we know that PIV is V diode maximum. Okay, this was 2 Vm sine alpha maximum value. This will be equal to 2 Vm. So PIV is larger than half wave rectifier. Okay, so this is important. So we cannot, this is not suitable for this is not suitable, so the design of center-tap full wave rectifier is not suitable with the diodes having the breakdown voltage less than 2 Vm. Okay, so this is basically a major drawback. You can see it's a 2 Vm, which is higher than the half wave rectifier. So there are some limitations, there are some advantages of full wave rectifier over half wave rectifier and vice versa. Based on those concepts, we will basically move on to the bridge rectifier, bridge full wave rectifier, which basically nullifies all the limitations of full wave center-tap full wave rectifier and half wave rectifier, which takes care of all the problems. Okay, that we shall discuss in the forthcoming sessions. of the lecture. Okay, so the 14th point of discussion is, so greater PIV means is a disadvantage, a greater disadvantage. So you can say it's a disadvantage. It's a disadvantage of standard at full wave rectifier. We'll discuss about the form factor, which is defined by F. So we define a form factor as, now form factor is defined as we already know, it is defined by IRMS by IDC, where ripple factor is defined as IRMS dash by IDC. This is a total. So IRMS for this is equal to IM by root 2 upon IDC being 2IM by pi. So if you solve for this, you get F as 1.11. okay, so this form factor value was 1.57 in the case of half wave rectifier, and ripple factor was 1.21. so here the ripple factor has reduced by a drastic change. There is a drastic change in the ripple factor in the full wave rectifier as compared to the half wave rectifier, because it is equal to 0.483 in the full wave rectifier and is equal to 1.21 in the half wave rectifier. Form factor is also reduced. It was 1.57 and it is now 1.11. okay, now there are the major differences that you should know and we should be able to point out. Now next point of discussion is frequency of the output voltage. So basically if we basically represent the output signal in terms of its Fourier series expansion, so we get V naught. It is basically 2 Vm by pi minus 4 Vm by pi summation k being even cos k omega naught t upon k plus 1 into k minus 1. This is how you represent. This is basically your DC, this is basically your AC, while that was equal to Vm by pi plus Vm by 2 sine omega naught t minus 2 Vm by pi summation k being even cos k omega naught t upon k plus 1 into k minus 1 in case of half wave rectifier. And this is this 2 Vm by pi minus 4 Vm by pi cos k omega naught t. So the minimum frequency minimum frequency present in the expression is basically 2. So if k is even, so we cannot basically place 0 in this case, because cos 0 is already 1 and that is already our DC value. So if we just, the minimum value being cos 2 omega naught t upon 2 minus 1 upon 2 plus 1, so the minimum fundamental frequency, the fundamental or ripple frequency in this thing is 2 omega naught or 2 f naught. Okay, and time period being t naught by 2. Understood? So AC component basically consists of harmonics, because this is, the output is not sinusoidal. Okay, so in this case, since frequency is 2 omega naught, filtering becomes easier. Filtering of the output becomes easier since frequency has been doubled. It is 2 omega naught, so that's why frequency, it is easier to filter the output signal. So if we basically neglect the higher frequency components, if we neglect neglecting higher frequency components. So we get V naught as 2 Vm by pi minus 4 Vm upon 3 pi cos 2 omega naught t. We can approximate this thing to this. Okay, so we can represent a full wave rectifier with this small circuit without even considering all other parameters. We can just replace it with one DC voltage and one AC voltage, and then we can calculate whatever you want to calculate. Okay, this is how it looks: 2 Vm by pi upon 4 Vm upon 3 pi cos 2 omega. So we can say a center tapped full wave rectifier is approximated to a series combination of a DC and AC voltages. Okay, we can consider this thing. So how can we represent it? We can represent it with a DC and an AC voltage. Okay, and we can take the output voltage here. So this is VDC, which is 2 Vm by pi, which is DC, AC being 4 Vm upon 3 pi cos 2 omega naught t. So this is how it looks. This is how it will look. Okay, so this is basically the equivalent of full wave rectifier. Okay, now next point of discussion is the angle of conduction. Angle of conduction. Angle of conduction. So angle of conduction is basically the period for which your diode conducts. The period for which your diode conducts, and it will conduct only if the voltage crosses the cut-in voltage of the diode. We are not considering an ideal diode. We are considering here a practical diode, and we are only considering your gamma value, V gamma. So it will only conduct it when your input voltage crosses your gamma, which is cut-in voltage. So if we just say if the diodes are ideal, so if the diodes are ideal, so we have to basically consider both diodes in this scenario. So let me explain to you. If the diodes are ideal, each diode conducts for 180 degree, so total conduction angle will be 360 degree. Okay, while if non-ideal diodes are considered, then each diode conducts for 180 degree minus 2 theta angle. So total conduction angle will then be 360 degree minus 4 theta. So if we just have a look at VA, it's something like this, and VB, it's just the negative of it. Okay, so when VA crosses this particular V gamma, this is V gamma, this is also V gamma, this is VB, this is corresponding diode D1, this is corresponding to diode D2, this is alpha, this is alpha. So this angle is theta, this angle is 180 minus theta, and VB conducts for this is theta, this is basically 360 minus theta. Okay, this will be 360 minus theta. So if we consider all the angles, this is 180 minus 2 theta, this is also this thing. So 180 minus, if we just solve for this, we get 360 minus 4 theta. Understood? This is how it goes. This is theta, this is 180, let's say theta. Okay, we are considering theta here. This is 180 plus theta, and this is 360 minus 180 plus theta. Okay, so if we just consider, so this is basically 180 minus 2 theta. This is also 180 minus 2 theta. This is basically 180 plus theta. This is 360 minus, so we can say it is 360 minus 180 plus theta. You get 180 minus 2 theta, and the total angle, conduction angle being 360 minus 4 theta. Where theta is sine inverse V gamma by Vm. Okay, so your D1 conducts for 180 minus from theta to 180 minus theta, and D2 conducts for 180 plus theta to 360 minus theta. Okay, make a change here. This is 360 minus theta. So this is how it looks, 180 plus theta, with the total and conduction angle being 360 minus 4 theta. Now next point of discussion is transformer utilization factor, TUF. 17 point is TUF, or the transformer utilization factor, TUF factor. So transformer utilization factor is basically the ratio of AC, ratio of the DC output power to input AC power rating of the secondary transformer, secondary winding of the transformer. So we can say, we just have a look at this, that full wave rectifier is a combination of two half wave rectifier. Therefore TUF with respect to secondary winding, will be double to that of half wave rectifier. So you can say that TUF for secondary with respect to secondary winding will be 2 into 0.286 RL divided by RL plus RF is equal to 0.572 RL by RL plus RF. Okay, so we can say that TUF of secondary winding, it is equal to 0.572 RL divided by RL plus RF. But so if we just find out the TUF with respect to primary winding, if we find it with respect to the primary winding, so we can define with respect to the primary winding as DC output power divided by AC power rating of primary winding. So it is equal to IDC square into RL. Now AC power rating, it is equal to Vm by root 2 into Im by root 2. Okay, this will come out to be IDC square into RL Vm Im by 2. Okay, so basically it is Vm1 Im1 This will be equal to Vm Im, because we know that Vm1 Im1 will be equal to Vm Im. This is across the primary winding, and since the turns ratio will cancel each other, so Vm Im1 is equal to Vm Im. Okay, so Vm1 and Im1 will be equal to Vm Im. So we can write, if we plug in the values, the tuff with respect to the primary winding will be equal to 0.81 RL divided by RL plus RF. So we can say average tuff will be equal to 0.572 plus 0.81 divided by 2 is equal to 0.69. So average tuff for a center tapped half wave full wave rectifier is 0.69. Again, this is most important with respect to IES exam. Okay, so yeah, now the next point of discussion, let's now discuss about some of the advantages and disadvantages of full wave rectifiers. So let's discuss first about the advantages of it. Okay, so yeah, first one, it has smaller ripple factor, or you can say suppressed AC ripples, more seamless, more smooth DC with respect compared to half wave rectifier. Second one, it has greater efficiency, because the efficiency of a full wave rectifier is double to that of a half wave rectifier. It is 81%. Maximum efficiency is 81% when we consider the ideal diodes. Third, greater DC output current and voltage, because we know that VDC-FL in this case, VDC-FL is 2 Vm by pi minus IDC into RSW by 2 plus RF, and the half wave rectifier it was Vm by pi, so we can say VDC-FL greater DC output voltage. Okay, and similarly your IDC or output current, which is 2 Im by pi, it is double to that in the case of half wave rectifier. So greater DC output current and voltage. Fourth point, filtering of AC component is easier in the full wave rectifier, because fundamental frequency is not present or cancelled by rectifier. Okay, and it has greater tuff. Understood? So because the frequency here is 2 omega naught, so filtering is more seamless as compared to that in the case of a half wave rectifier. Now let's have a look at the disadvantages of a center tapped full wave rectifier. There are always okay, the first one is greater PIV, or diodes with higher breakdown voltages are needed, or you can say diodes with the higher breakdown voltages are needed, which is of course a major drawback, because greater PIV means if we use if you use the diodes with the, if you use the cheaper diodes, or we can say if you use the diodes with a lesser breakdown voltage, cannot bear greater PIV in, okay, cannot bear greater PIV, and that could basically damage the diodes. So obviously we require diodes with a greater breakdown voltages, which are of course costlier than the counterparts. Second one, it is necessary to use center tapped transformer which is bigger in size, and costlier too. Okay, so above disadvantages are basically nullified in the case of bridge rectifier. Okay, now let's move on. So this is enough for the center tapped full wave rectifier. Now it's the time to start a new topic of discussion. It's a bridge rectifier. Okay, there are many properties that we need to understand of a bridge rectifier, and we shall discuss all the advantages, all the properties of bridge rectifier, and how it basically supersedes the center tapped full wave rectifier. Okay, so the basic diagram of the connection diagram of a bridge rectifier looks like this. This is pure AC signal. Okay, this is basically step down transformer, is N1 is to N2. Now this, okay, so you should be careful with the diagram of a bridge rectifier. It is like this. So let me just draw it so that it is more clearer to you. This connection is here, and this connection is like this. Okay, this is RL, this is VO, this is VI. This is basically a step down transformer where you can say that N1 is greater than N2. Okay, this is the output voltage taken, and this is how a bridge rectifier looks. It's again a full wave rectifier, bridge full wave rectifier. How it works, let me explain you the operation. Okay, so if we just have a quick look at the waveforms, this is alpha, this is alpha, this is VI, and here it is VO. So let me draw this thing. So your input voltage basically varies like this. Okay, and your output will be like this. It's again a full wave rectifier. It's basically a pulsating DC. Okay, it's basically a pulsating DC. It's a pulsating DC. This is 0, this is pi, 2 pi, 3 pi, 4 pi. This is 0, pi, 2 pi, 3 pi, and 4 pi. Now case 1, when alpha lies between 0 and pi. Let us just quickly discuss the operation of a bridge rectifier. When alpha lies between 0 and pi, what happens? When alpha lies between 0 and pi, Vi is positive. Vi is positive. Since Vi is positive, let me basically demarcate these diodes as this is D1, this is, let's say, D2, this is D3, and this is D4. So when alpha lies between 0 and pi, what happens that Vi will be positive. Since Vi is positive, your diode D1 and D3 will be forward biased and will be short circuited, while your D4 and D2 will be reverse biased. So we can say that in this case Vi is positive. So you can say that D1 and D3 are forward biased, while D2 and D4 are reverse biased. This is open circuited and these are short circuited. Okay, so we can say that the current flows in this particular loop. So this is short circuited. The current flows like this. So current flows occur through a loop consisting of D1, RL and D3. So the current flows like this. This is how the current flows. So current will flow like this. You can say the current flow will be like this, like this. This is how the current will flow. So current flows in the loop consisting of D1, D3 and RL. Okay, so the current direction will be, this is the direction of the current for the first case. Now if we consider another case, the other case, case 2, when alpha lies between 2 pi and pi. When alpha lies between pi and 2 pi, what is in this case? So if we just quickly have a look, let me write it with green. In this case Vi is negative, and in this case D2 and D4 are forward biased. Your D1 and D3 are reverse biased. They are open circuited and they are short circuited. So the current basically flows in the loop. So in this case your D4 and D2 will be forward biased. Okay, so the current flow will be like this. Okay, so if you keenly observe that the current flows like this for the second case, and current flows in the opposite direction to this current as in the first case. Okay, this is for the second case, this is for the first case, and this is for the second case. So we can clearly observe here, that both the currents are basically opposite in direction, opposite to each other. Hence we can conclude that through the transformer, through the secondary winding of the transformer, there will also be an AC current flowing. There is no DC current flowing. Okay, there will not be any DC current that will flow across the secondary winding of the transformer, because both the currents are basically opposite in the direction to each other. They have a phase shift of 180 degrees. So net current is basically an AC signal, is an AC current. So if we consider your when we will consider your total internal voltage drop, which is IDC into R, and we used to write R is equal to RSW by 2 plus RF in the case of center at full wave rectifier, because there we considered that there will be a DC power dissipation across the secondary winding, because a DC current also flows through the secondary winding of the transformer. But here in this case there is no DC current flow that will flow across the secondary winding, so we will take RSW equal to 0. So from here we can conclude that, so let me just write it here, that current flows in the loop consisting of D1, D3, sorry, it's D2, D4 and RL. Understood? So current from here, you can say current through secondary winding, current through the secondary winding is bidirectional or AC. Okay, current through RL is unidirectional. It is unidirectional or pulsating DC. Pulsating DC, because it always flows in one direction or downward direction, we can say. Okay, so as we already saw, the current flowing both directions, you can say, is in the downward direction. So current flow is always in the downward direction across the resistance RL. So that will always be there will be a DC component present at the load resistance RL. Okay, so that's all, folks. I am stopping this lecture here. Please go through all the concepts that I covered thoroughly and be well versed with them. Thank you very much, and please, if you really like this video, please hit the like button and share and subscribe to our channel and hit the bell icon for the latest updates. Thank you very much.